As the global divide between demand and accessibility to clean water continues to widen, we need to ask ourselves, how are we going to prepare for a world where we don't have enough of its most valuable resource? And what will the world look like if we remain complacent? With the shifting climate patterns, increasing levels of pollution, and population growth, water scarcity will affect both developed and underdeveloped countries alike. Luckily, brackish groundwater resources are in abundance not only in drought-prone inland regions of the United States, but also in many other water-stressed regions of the world. If treated cost-effectively, brackish groundwater can become an alternative water source for many communities that already started experiencing the adverse effects of climate change. Currently, existing technologies for desalination, such as reverse osmosis and electrodialysis, are mostly optimized for seawater desalination, where the produced brine can be safely recycled back into the ocean. However, for inland desalination applications, safe disposal of brine becomes a major cost driver. Hence, development of energy-efficient desalination technologies with high water recovery rates is of critical importance. In the Gadgil Lab for Energy and Water Research at UC Berkeley, we are relentlessly working to address this problem by developing an electrified, modular, and highly cost-effective brackish water desalination technology that can achieve high water recovery rates. In our patent-pending two-step desalination system, we use stacks of interconnected electrochemical cells that can be arranged in various configurations to meet specific ion removal performances. In each reactor cell, two flowing streams of high ion capacity slurry electrodes are initially pumped into an ion capture stack. These slurries are formulated using a blend of ion exchange resins and functionalized activated carbons in water and can be tailored to target specific ions by changing the slurry formulation. Brackish water enters the center channel of the ion capture reactor and leaves the system as desalinated fresh water. During this process, with the applied potential, slurry electrodes attract salt from the water and eventually get saturated with ions. Saturated slurry electrodes are then pumped into a secondary regeneration reactor, where the reversal of the applied potential forces the absorbed ions back into the center channel, producing a highly concentrated brine stream, and also allows partial recovery of the energy that was initially supplied for desalination. Our patent-pending reactor unit contains intricate flow field designs that maximizes the interface between water and the slurry channels, which offers the optimal balance between water recovery and pumping efficiency. As demonstrated by the modularity of our stack design, the size of the system can vary from a handheld unit for personal use to the size of a shipping container for industrial applications. In addition, these stacks can be operated in parallel and series configurations where the performance can be easily adjusted towards the output needs of the application. We are designing our system with the needs of inland desalination applications in mind. Brine disposal is the most costly aspect of remote desalination applications. Thanks to our smart reactor design, we can reach up to 90% water recovery. Moreover, unlike reverse osmosis, our technology seeps out ions from brackish water by using differences in electrochemical potential of adjacent solutions. Therefore, the mass transport across the membranes is relatively low and does not require high hydraulic pressures to operate. As a result, efficient desalination in dilute concentrations becomes economically viable. Lastly, the modular stack design of our reactors and the flexibility we offer in slurry formulation allows easy customization of the desalination performance towards the quality of the water. Our revolutionary electrochemical desalination technology offers an affordable, scalable, and sustainable solution to desalinating low-concentration brackish groundwater sources. With the support of the CERC-WET program, backed by the Department of Energy, we are continuously testing and improving our desalination technology to improve the efficiency and further drive the costs down for rapid commercialization and scale-up. As the adverse effects of climate change on our water economy continues to worsen, increasing access to non-traditional water sources and creating a circular water economy is a national priority. Therefore, in the Gadgil Lab, we believe in the power of applied sciences, and every day we're pushing the limits of engineering to make a true impact in creating a sustainable world.